Can you see a cystic fibrosis document?
Yes.
Yes.
You can see it, all right. I have to turn my volume up because I can't really hear you very well. Okay. You should all have a copy of this. Has several URLs, which are useful. And then it has investigating CFTR mutations for your cystic fibrosis project. And it gives you a main website there. And then a list of mutants to choose from. You can choose any one of those to do your project on. And so the instruction here is once you've chosen a mutant, you can go to the website, enter your mutant, and start to research it. And what you will probably end up doing is finding some of the information you want on the website or other websites shown here, or you may have to look online elsewhere for some of the information you might want. Now, for your project, the guideline is make some PowerPoint slides. And first, show the effect of your mutation on the structure of the CFTR protein. And then secondly, show the effect on the function of your protein. And then indicate the disease symptoms that your mutation causes. And then, if there are any, indicate possible treatments for the symptoms caused by your mutation. So I'd initially said that each student would have 90 seconds, and then I began to realize that was ridiculous. So I've extended the presentations over the course of 2 class periods, and I've given each student a total of 4 minutes. We'll have to be pretty strict about the time, or we're going to run out of time. So I will tell you when you've reached 3 minutes, and that will give you a minute to finish up, and you have to finish by 4 or I will stop you at that point. Now, something I'm wondering, can you all share your screen with the rest of the class? Like if we were doing presentations right now, can you share your screen and put your presentation up?
We can, but you have to give us permission, like in the settings.
All right. Do you know specifically what setting I have to change?
I believe it should be under like meeting settings, and then you have to go to like screen sharing, and it should say allow everyone to share.
Okay. All right, I will look for that and try to make that change before Monday so that you can all share your screens to make your presentations. Okay. Then your presentation will be worth a maximum of 50 points, and I'll grade them as we go. As you make your presentations, I will grade in real time according to these criteria. And then farther down this document, I have the schedule of your presentation. So half of you will be going on Monday, the 30th, and half on Wednesday, December 2nd. You can see your names there. If I've missed anybody, let me know. Okay, any questions about how to proceed with your presentations? I know some of you have started already. And whether you have or haven't, you need to be ready by either Monday if you're a Monday presenter or Wednesday if you're a Wednesday presenter.
Professor,
Yeah.
I was curious if we had to like turn on our cameras, because I know my internet gets a little bit wonky whenever I have to turn on my camera. So can I just do the presentation with my voice, or do I have to turn on the camera?
Oh, it would be much better if you turned on the camera, because, or if you're screen sharing, you have to have your camera on to share your screen?
No.
No,
Okay.
you do not.
Okay, then that's all we care, is to be able to see your presentation and hear your voice.
Okay, thank you.
Okay, anything else?
I do have a question.
Yeah.
So it says to prepare 2 or 3 at most PowerPoint slides, and says effect of your CFTR mutation on protein structure. Is the protein structure our mutation?
Protein structure is, okay, so you've got a certain nucleotide sequence for the CFTR protein, a certain amino acid sequence for the protein, and now you have a mutation in it. And so what I want you to show is what that mutation does. So if it's a deletion, what's missing? If it's a base substitution, what is the substitution? That's all I mean by that.
Okay.
Any other questions? Because I have sort of a little model presentation I thought I would go through to give you an idea of how I would approach this project. So any more questions before I go to that? All right, then I'm gonna...
For Scott's workshop, will that be going on today?
Scott?
Yes, I do intend to have a session today.
Okay, that will be at 2 o'clock. Now you should be able to see Cystic Fibrosis Mutant Analysis Project. Anybody can't see that? It's on slideshow. So I looked at the list of mutants, and I arbitrarily, with no forethought at all, chose a particular one, R117H. So what is the structure of my mutant? Well, it's a missense mutation, which means that there's a single base change from G to A. And this causes a single amino acid change from CGC, which is arginine, to CAC, which is histidine. And here you have a partial amino acid sequence indicated by one-letter symbols of the CFTR protein. And this red R here is the arginine that is changed to a histidine in the mutant. So what is the effect of the mutation? It causes incorrect folding. So there's an altered tertiary structure. And you remember how critical the tertiary structure is for the protein function. So that's the next part. What is the function, and how is the function of the protein changed? Well, with wild type over here on the left, you have the protein made, inserted in the plasma membrane, and it transports chloride ions. Now this mutation, you see it's R117H is listed here. So it's a type 4 mutation. And what it does, it makes the protein just fine, but the protein is defective. So instead of transporting the normal amount of chloride ions, it transports a reduced amount. Now this is the next part. What are the symptoms of this mutation? Well, pancreatic insufficiency, about 85% of the people who have this mutation have symptoms. Lung function is not affected much at all, from 65 to 123% of normal. About 55% of patients get Pseudomonas infection, and it's likely that the chloride in sweat is elevated a little bit from 60, which is normal, to 74 milliequivalents per liter in a mutant. So of the two organs most affected by cystic fibrosis, lungs aren't affected much. The pancreas is affected a lot. And here you see on the right a picture of a real pancreas from a cystic fibrosis patient. And the duct is this object here, and you can see the mucus accumulating in the duct, which then blocks the flow of the pancreatic juices. What are the molecular symptoms of this mutation? I have a diagram here on the left. So in normal CFTR proteins, you can see this illustration of the protein in the membrane. Each one has a channel, and each one has a gate. Now in the R117H mutation, this channel is narrow, and this gate is closed most of the time. It only opens occasionally, and between these two, that's what slows down the transport of chloride ions. So there's low chloride ions outside the cell, which means there's low water content. And without the water, the mucus cannot wash away properly. And you see that in this diagram, this picture on the right, was a normal channel releases chloride ions and mucus accumulates when it doesn't. And the last part is, what is treatment? Well, there's a chemical, a medicine called Calideco, produced by the Vertex company. It treats 10 different mutations in the CFTR gene, including R117H. And what's the effect of this drug? It widens the channel and opens the gate. So we go back. The problem is that this channel is narrow. The gate tends to remain closed. And what this drug does is open this channel and keeps the gate open more of the time. There are a whole lot of possible side effects. I won't go through them all, but that's it. I don't know how long that took me, but it was supposed to be 4 minutes or less. So any questions? That is sort of a model treatment. You certainly don't have to adhere to this. I'd like to see you use your own imagination and ingenuity in constructing your own presentation. But I just wanted to give you an idea of one way that it could be done. Any questions about what I just did?
Could we have more slides than 3? Because I've pretty much finished my presentation and all the information, but I don't have any room for pictures.
Yeah, you can have any number of slides that you want. The main problem that you might run into is time. So you can't go more than 4 minutes. And so talk your way through your presentation before class and time it so that you know that you won't be going over 4 minutes. But no, the number of slides you use is up to you. And so, for example, instead of packing a whole bunch of stuff on one slide, you might want to distribute it over 2 or 3 or 4 slides and simply skip through them faster.
Yeah, I just asked because the I believe the directions say a maximum of 3 slides.
Well, yeah, I didn't get around to changing that. That was when I thought I was going to give you 90 seconds. That just wouldn't work. So with 4 minutes, you can relax a bit. Okay, any other questions? Then I will stop sharing this screen.
Professor,
Yeah.
on your first slide, it showed the protein structure effects of the CFTR mutation. And did you use one of the websites to find the information on that?
That I think I went into the National Library of Medicine to get that sequence. The website for that, if you remember, we had a lecture on CFTR and its mutations. And I think that one of the slides in that lecture had a website to NCBI. So you can either just look it up, or you can go to that, that slide in that slide set, and it should take you right to the sequence of the CFTR protein. Anything else before I change the subject? Can you see energy sources? Should
Yes.
be. All right. I wanted to do this because we've been talking about energy. Energy as it relates to biology. But on this planet, there's a much, and also a very large issue about energy in general, not just for keeping things alive, but generating electricity for all the needs of a civilization. And this, because the energy needs have gotten very large, it's caused us to have a climate crisis. And that is a serious problem that nobody knows how it's going to end up. But right now, it doesn't look good. So I thought it was worth taking time in this class to talk about, at least my view, of energy sources and what we should be trying to do to ameliorate the problem of climate change. So, the top of this slide, energy sources can be either combustible or non-combustible. If they're combustible, to get energy out of them, you have to burn them. And when you do, you release carbon dioxide. Non-combustible, obviously, you don't need to burn it and you don't release any carbon dioxide. So this should be the goal then, to convert most of the sources of energy that we're using now are combustible. And what we should be doing is switching as fast as we can to non-combustibles. If you just look over a long period of time, from 1880 to the present, the global temperature has risen dramatically. And one of the goals of climate change people right now is to keep the temperature increase compared to the pre-industrial revolution time less than 2 degrees centigrade. Here you can see it's up to 0.6. So this is how CO2 in the atmosphere has varied over a long period of time, 800,000 years. So you can see it's gone up and down and up and down over the years. And it's only at the present time that it's gone out of sight. And what is the main problem? It's carbon dioxide, by far. You've probably already all heard of the greenhouse effect. What is it? Well, it's caused by mainly carbon dioxide, but also other gases in the atmosphere that trap heat. So when the sun shines on the planet, some of the energy is absorbed, but a lot of it is reflected back out into space. Well, if gases produced on Earth make a layer in the atmosphere, it interferes with the escape of heat from the planet. It's trapped here, and that's called the greenhouse effect. Because that's what happens in a greenhouse. You can have a greenhouse on a sunny day, it's unbearably hot, and that's why. The heat from the sun is trapped. This is both the carbon cycle and the unbalanced carbon cycle. So normally, without human disturbance, if you look on the right, plants, green plants, undergo photosynthesis, and when they do that, they fix carbon. They take it out of the atmosphere. Then animals eat the plants, and if you go over to the left, animals respire, and when they do, they release carbon dioxide, and you see that plants also respire and they release carbon dioxide. Now, without humans, that cycle is balanced. So the carbon dioxide in the atmosphere is fixed, and then it's released, and it just continues this cycle. Human activities have unbalanced it. So now we have mainly the burning of fossil fuels, which releases carbon, and there's deforestation worldwide that releases carbon dioxide. And so the increase in release is much greater than the capacity of plants to fix all this carbon. And so we have this imbalance. Atmospheric carbon dioxide goes up, we have the greenhouse effect, and the planet warms. So this is how it happens: burning, combustion, and its effects. So just an example of burning a combustible substance, I've taken gasoline. We all use it. A main component in gasoline is octane, which is this molecule. It's a hydrocarbon. So what happens when you drive your car is that a molecule of octane and 25 molecules of oxygen make 18 molecules of water and 16 molecules of carbon dioxide, plus energy. So it makes your car go. So this is the process by which we generate carbon dioxide. So in addition to global warming, CO2 contributes to the ozone layer depletion. The ozone layer helps protect us from the damaging radiation from the sun, acidification of the environment, ecotoxicity, and human toxicity. The effects of global warming, you're all aware of these things. I'll run through them quickly, but sea levels are rising. And as the polar ice melts, the sea level rise to about 20 feet by 2100, and entire nations are going underwater as we speak. It's a big issue for the United Nations, what to do about the people in these countries whose countries no longer exist. Extinction 30% of plant and animal species are likely to be extinct by 2050 due to loss of habitat. So for example, polar bears will become extinct. There's nothing we can do to save them. They depend on ice, and the ice is going. Plant and animal behavior changes, human health and welfare. There's a lot of diseases that are related to climate change. Storms, we're very aware of storms, all the storms we've had this season just in the US alone, on the southern and eastern coasts, also in Central America. Storm frequency is increased, and the strength of storms tends to be increasing. At the same time as we're getting storms, we're getting droughts. For example, the west, southwest of North America is in a more than 10-year drought period right now. Economic collapse as governments try to bear the cost of remediation. Just think of the cost to our government for all the damage done to cities along our coast by storms. Ecosystem failure and even wars result from climate change as resources become limiting. Nations are inclined to do drastic things, like, for example, the genocide in the Darfur region of the Sudan. Right now, there's a war going on in Yemen, supported by Saudi Arabia, and it's causing huge problems for the population there. So here's an example of the urgency, sea level rise. So this is hypothetical, this map. What if all the ice melted? If all the ice on both polar ice caps melted? Well, look closely and you can see a blue outline here of the eastern and southern coasts of North America. That's the present day shoreline. If all the ice melted, the shoreline would recede to what you see in the other colored part. So the entire Atlantic seaboard would vanish, including Florida and the Gulf Coast. In California, San Francisco's hills would become a cluster of islands. The Central Valley would be a huge lake. And the Gulf of California would extend north of San Diego. And on the right here, I have a picture of an island as it used to exist and what it looks like now. This is somewhere in the South Pacific. Global sea level has risen 8 inches since 1870, projected to go as high as 56 inches, depending on where on the planet you are, by 2100. Asian countries are at greatest risks, and as I emphasized earlier, entire nations, islands and entire nations are disappearing, and we can't stop the ice from melting, so we can't stop these islands from going underwater. There are 3 main classes of energy source: fossil fuels, renewable fuels, and renewable fuels that are combustible and renewable fuels that aren't combustible. Most of our energy worldwide now comes from fossil fuels. They're non-renewable and they're combustible. A small amount comes from renewable fuels, but you have to burn them. So for example, ethanol, biomass, anything that you have to ignite to get the energy out of it is combustible, and it generates CO2. Only a small amount of worldwide energy consumption comes from non-combustible fuels: wind, water, geothermal, tidal, and so on. The essential point here is that carbon dioxide accumulation will end or slow down only when the sources of it are reduced or eliminated. So the goal then is to replace combustible fuels with non-combustible ones. Here I just put in a bunch of pictures of the various different types of non-combustible energy sources. So the tides, you can put machines in the water that will extract energy from tides or from waves, solar panels from the sun, turbines for wind. We have dams that can generate hydroelectricity, geothermal power, nuclear power. A significant amount of energy used today does come from nuclear power. The good thing about nuclear power is that it's non-combustible. All right, so how do things look for the future? Well, looking worldwide, Germany stands out. And here is one of the reasons. Net public electricity generation in Germany this year in 2020. About 55% of it comes from non-combustible sources and the rest from combustible. So what are the non-combustible sources that Germany uses? Well, nuclear power, uranium, 12%, solar power, get this out of the way, 11%, wind, 27%, and hydropower, about 4%. Now, biomass is combustible, so that doesn't count. Where do they get the rest of it? From soft coal and hard coal, oil and gas. But Germany is a model for the rest of the world to look at. How do they do this? And a large part of the reason they can do it is that they do a lot of grassroots work with people and communities, convincing them that it's in their best interest to adopt energy sources that are non-combustible. Now, Germany has a lot of wind, but they don't have a lot of sun. Yet they produce 12% of their electric energy from the sun. So they have very efficient ways of extracting energy from sunlight. Compared to the United States, in 2020, we have, rather than 55%, 38% non-combustible, combustible 61%, and this is the distribution of, in 2020, about 15% solar, 38% wind, 2% geothermal, and 37% hydroelectric. So compared to Germany, the US is far behind. What about electric cars? Cars are one of the main sources of carbon dioxide. So this shows number of countries in the world and the percentage of cars that are electric. Norway is way ahead of everybody. 56% of their cars are electric. And then it drops off real fast after that, and you go way down and down and down. United States is down at 2%. So we have a long way to go to reduce pollution from cars. Okay, looking forward. What should we be trying to do? And I am being nowhere near comprehensive in this, but there are some simple things that could be done rather quickly to speed up the process of reducing carbon dioxide production. So for example, the US government subsidizes the fossil fuel industry over $300 billion a year. For what? If this money were going into improving the efficiency of non-combustible energy, it would make a huge difference. Many countries are now putting a tax on carbon. There's such a thing as a carbon footprint. Each of us has a carbon footprint. It's a complicated formula, but it's an indication of how much carbon our activities generate on a daily or yearly basis. So that could be taxed. It can be readily quantified and taxed so that the more carbon you produce, the more tax you pay. Now we have a new administration coming in, the Biden administration, in January. One of the things they've said on day one is that they're going to rejoin the 2015 Paris Climate Agreement. As I indicated earlier, one of the goals in that agreement is to keep carbon dioxide increase so that the global temperature, keep the CO2 increase low enough that the global temperature will not rise more than 2 degrees centigrade above pre-industrial levels. That, according to people who study this, is the cutoff. If you go above 2%, then probably environmental disaster would occur, and it's hard to predict what would happen after that. So if this goal can be reached, many people think that disaster can be avoided. Carbon sequestration. There are ways now to capture carbon and put it underground, just get it out of the atmosphere. Economically, it would be a good thing to transition jobs. We don't want to put people out of work. We'd like to transition people who are now making their living with fossil fuels, for example, coal mining or fracking for gas, and convert their efforts to high-paying jobs in clean energy. And right now, that's mainly wind and solar. And one thing that's desperately needed, and nobody that I know seems to have an answer for this, is how to store energy. Fossil fuels are stored energy. So it's easy to store them and then get the energy out of them whenever we want to burn them. Other sources, non-combustible sources of energy, for example, wind and solar, which you see here on the right, the wind doesn't always blow and the sun doesn't always shine, and yet your need for energy continues. And right now, from what I know, the best batteries we have are lithium-ion batteries. They're good, but they function just like a lead-acid battery, except they're more efficient. And so we have these battery farms where huge numbers of batteries are used to store energy for when we can't get it from other places. This is a graph of battery storage capacity. It's increasing, but the increase is not due to improved technology so much as it is just more of them. We're making more and more and more batteries. And this brings us to something we've talked about before, the laws of thermodynamics. And I've alluded to this, but I'd like to say it explicitly, that the problem we face is that fossil fuels are so convenient because the energy in fossil fuels is concentrated. It was concentrated millions of years ago by photosynthesis. So plants harvested sunlight, made carbon compounds, and stored it. And now we mine it and ignite it, and we get immediate heat and light. So that's a very nice thing about fossil fuels. In contrast to renewable energy, which is too diffuse to do work as we receive it. So we receive sunlight, we receive wind power or tidal power. It's not really concentrated enough to do work. We have to concentrate it first. So we can do that with solar panels, we can use wind turbines, but it's technologically much more of a challenge than it is to light a match and burn a fossil fuel. So that's the challenge that we face in trying to convert from combustible fuels to non-combustible. But as I was trying to point out, there is hope. I mean, there are many wind farms, there are many solar panel farms, especially across the southwestern United States, but actually across the entire country. And a lot of these wind farms are built offshore, which depends on your point of view. It may be a good thing to get them out of people's backyards, or some people object to having them anywhere because they're considered unsightly. I happen to think they're beautiful. And when you see them actually when they're working, when the turbines, the blades are turning, it's really quite a sight. All right, that's my spiel on energy and climate change. Anybody have any comments, opinions, questions about it? No, nothing? Some of you are still here. Okay, well, that's it for today then. You can use the rest of the period preparing or thinking about your presentations for next week. And don't forget, you can talk to Scott at 2 o'clock.
All righty.
Have a good Thanksgiving.
Scott, you'll be there at 2?
Oh, I wouldn't miss it for the world.
Yeah, well, and one of the things that you can help with, if people have issues with their cystic fibrosis presentations, you can help them with that during that period.
I probably could do that. Yeah. I got a kitchen full of women cooking things for tomorrow, so.
Well, unfortunately, odors don't travel electronically.
Well, that's okay. I'm staying out of trouble by staying out of the kitchen.
Yeah. Actually, I have to make a salad, a cranberry salad for tomorrow. I have a specialty that I do.
Mm.
Once a year, every Thanksgiving, I make cranberry salad.
I make two things, and one of them is I baked some sourdough yesterday for a sourdough stuffing, and then for Christmas I usually make ice cream and give it out to our neighbors as Christmas presents.
You've got an electric ice cream maker, I hope.
Oh, absolutely.
The reason I ask is that when I was a kid, we turned it by hand. That was killer.
Yeah, it is. No, I burn trees and stuff for that. So yeah, it's looking like it'll be another nice small gathering tomorrow. Mostly just family.
Yeah, well, I'll be going to a small one too. All right, well, you've got to get ready for your workshop. Everybody else has to get ready to go to it. And I have things I need to do. So I will sign off, and I'll see you all next week. and we will do presentations on cystic fibrosis.
Happy Thanksgiving, sir.
Yeah.
Happy Thanksgiving. Yep. Aye, aye, and let's get going.
Okay. Take care. Bye.
All right. Bye.